Radiation detectors. There are different types of radiation detectors. The first is photographic film. When radiations such as alpha particle, beta particles, or gamma rays hits the photographic film, the energy of radiations will cause the film to be exposed. Therefore, the film will be darkened. The degree of darkening effect shown on the film reveals or discovers the amount of energies that the radiations is being absorbed. That is to say, if the amount of radiations being absorbed increases, then the degree of darkening effect will increase, or we say it will be darker. As a conclusion, a photographic film is mainly used to measure the amount of radiation energies absorbed. The second type of radiation detector is called GM counter. A GM counter is composed of two parts. The first is a GM tube combined with a counter. When a radiation such as a alpha particles enters into the GM tube, the counter will register the radiation as a single count 1. Therefore, if there are 500 radiations such as 500 alpha particles or 500 beta particles or 500 gamma rays enters the GM tube in 1 second, the counter will register a measured count rate of 500 per second. That means 500 counts per second. As a conclusion, a GM counter measures the amount of radiations enters into the GM tube. The greater the count rate, that means the amount of radiations is greater. Note that GM counter is suitable for measuring beta and gamma rays because beta and gamma rays have high penetration power. Therefore, almost all the beta particles and gamma rays can pass through the thin mica and get into the GM tube. However, a GM counter is not suitable for measuring alpha particles. The reason is that because only higher energy alpha particles can pass through the mica, while the low energy alpha particles are stopped or absorbed by the mica. Therefore, not all the alpha particles can be registered by the counter. Or we say the lower energy alpha particles cannot enter into the GM tube and stopped by the mica. The third kind of radiation detector is called diffusion couch chamber or just say couch chamber. When radiations enters the chamber, these radiations will ionize the air molecules into positive and negative ions. At the same time, the alcohol droplets inside the chamber will attract towards the ions. Therefore, a cloud track is shown along the path of the radiation. Since the ionization power of alpha particles is very high, therefore the alpha track will be very thick. However, the range in air for alpha particle is small, only a few cm in air. Therefore, the alpha track shown will be short. However, for beta particle, the ionization power is low. Therefore, the beta track shown on the couch chamber will be thin. Since the range in air for beta particles is long, therefore the beta track shown on the couch chamber is long. Lastly, the ionization power for gamma waves is very weak or very low. Therefore, the gamma track shown on the couch chambers will be scattered or hardly seen. As a conclusion, by observing the couch track shown on the couch chamber, a couch chamber can be used to distinguish what type of radiations. Whether this is beta, alpha, gamma, or both. Let's compare radiation detectors. For photographic film, it's mainly used to measure the amount of radiation energy. The greater amount of radiation energy absorbed, the darker will be the film being exposed. For a GM counter, it's mainly used to measure the number of radiations entering into the tube. It measures the number of radiations. The greater the number of radiation entering the tube per unit time or per second, the higher the count weight. For a couch chamber, it's mainly used to distinguish, or we say to identify the types of radiations, whether this is alpha, beta, or gamma radiations, by observing the couch tracks. What is meant by background radiation? background radiations 背景輻射 is the radiations emit from the radioactive materials in the surrounding. The typical sources of background radiations are: first, building materials and soil, about 16%. This kind of background radiations is significant when you are inside the building. Second kind of background radiations is radon gas, emit from the ground and concrete walls, about 43%. This kind of background radiations is significant when you are inside the home and can be reduced by opening the windows to let the gas running out from the room. The third main source of background radiations is cosmic ray 宇宙射線 from the outer space, about 13%. It is significant when you are taking a trip using the aeroplane, or when you are hiking in an open area. And cosmic rays can be reduced when you are inside a covered area. Other kinds of background radiations is from foods and drinks, about 8%, and from medical X-ray tracks, which is about 1%. Note that usually the count weight for background radiations is small. For example, the background count weight in 3 consecutive minutes are 20 counts per minute, 22 counts per minute, and 17 counts per minute, which is very small. However, the background count weight or the count weight will fluctuate. The small fluctuations of count weights are due to the decay of a radioactive source is random decay. This word is very important. The fluctuations of count weights are due to random decay. 隨機衰變. Let's see why alpha, beta, and gamma radiations are hazardous to human body, or they are harmful to our body. When radiations enters into our bodies, the ionization power of alpha, beta, and gamma radiations will damage the healthy cells. This makes mutations 變種 of the cells. Therefore, cancer cells will be produced. When placed outside our body, which radiation is the most harmful to our health? Why? When the radioactive source is outside our body, gamma rays will be the most harmful to our health because gamma rays has the highest penetrating power. Therefore, all the gamma rays can pass through our body and damage the cells. Next, if the source is placed inside our body, which radiation is the most harmful to our health? Why? If the source is placed inside our body, then alpha particles will be the most dangerous, because the ionization power of alpha particles is the highest. Therefore, more healthy cells will be ionized and cause cancer cells. Radiation dose, 輻射劑量. The effective radiation dose is measured in the unit of sieverts, SV. Notice that 1 millisievert equal to 10 to the power negative 3 sievert. Let's see some typical radiation dose under different environments. If you are flying at a height of about 9,000 meters for 1 hour, then the effective radiation dose absorbed will be about 0.001 millisievert, which is very small. If you take one X-ray track, then you will absorb about 0.01 millisieverts of effective radiation dose, which is again small. If you take 1 year dose from the background radiations, then you absorb about 1 millisievert of radiation dose, which is also very small. However, if you are near a leaking of nuclear power plant, 泄漏輻射嘅核電廠, then in 1 year or less than 1 year, you may absorb over 10 sieverts of radiation dose. That means this amount will cause fatal effect. Let's see some safety precautions when you are handling radioactive source. First, we should put the radioactive source inside a lab box to prevent the leakage of radiations from the source. Second, we may stick a warning label on the cover of the sealed box. Next, we should never point the source towards human beings. Next, we may use forceps to hold the source. Fifth, after using the source, you should wash the hands immediately. Next, wear thin patches to check the amount of radiations absorbed by the body regularly.